Right, okay. So how to design electronics. So let me, for anyone who's new to this party, let me just share with you. We started this is season 3, and it's really about my experience as an engineer. Been doing this for 30 years of just sharing some. Can I see your application? Oh, that's good. Got a message there. As I say, I've been in for 30 years. It's about me just sharing some of my ideas on engineering, electronics. Season 1 was basic electronics. If we gloss over anything, you might just want to skip back to season 1. They're all available to download, all these things that we talk about. Season 2 is microcontrollers. And this is season 3. We're going to be using the Raspberry Pi Pico that hopefully you can see on your screen on a development board I've made. And in particular, we're going to try our hand at doing some machine learning in MicroPython. And I've got some working, which would be brilliant to have a look at. So I'm just going to change this camera view to a PowerPoint, because I've done some slides on PowerPoint. Right, hang on a second. I've got to stop sharing. There's a chat message there. It's okay if I miss seasons 1, 2. Yeah, absolutely fine. If you didn't catch a session, don't worry, you can always ask questions. I might just refer you to something else. But yeah, no daft questions here. Oh, can I view record? Yes, it is recorded by MakeSpace, so that's not a problem at all. Right, hang on, let me just stop sharing. Let me just, that's all the housekeeping stuff, I think. Right, now then, fingers crossed. If I do a share screen on, I hope it's that. I'm now getting a bit frightened. This is all going to go very wrong. Right. So, can you all see that? Okay.
I love the graphics.
Yeah, okay, right.
Very,
you can all
very
see it.
cool.
Do you like that? Do you like that?
I do.
Brilliant. Right, I'm glad you can see it. Right, I can now relax a little bit because now technology is probably going to play for the evening. Right, okay, that's the intro. That's a picture of me. This is all done with MakeSpace. Right, so if I press that, hopefully. So if you all the slides we've got in this session, so if you do need to nip off early, everything's available to download. Just hop onto my website there, and season 3, all these slides are available to download. The MicroPython code, which we're going to be having a look at, that's all available to download, and you might find some other Easter eggs, goodies. It's actually there already, so you don't need to take any notes or anything. You just kick back with a cup of tea and enjoy the ride. Right, okay, let's move on, shall we? Right, so this session for us today is going to be all about a bit of temperature sensing, and we're going to try and apply some AI to it. So for those who aren't aware of what this AI stuff is, I've just got a quick little slide for us here just to set the scene. There's a number of artificial intelligence is very much it's an umbrella name of a number of different disciplines within it. And you can see from left to right, for some reason, someone in their infinite wisdom decided to have a subject of artificial intelligence under the umbrella name of artificial intelligence. There we go. Machine learning is very much what we're going to be looking at. Machine intelligence is machine learning is very much just maths at the end of the day, of just getting some data and trying to work out a graph for it, and then making a prediction thereof, and then trying to refine that graph from new data. Machine intelligence is really machine learning plus anything else to get the job done. So for me, I'm interested in machine intelligence, and that's one we're going to be playing with. Deep learning is all that neural net stuff, which we all hear about and makes the headlines. And artificial intelligence on the end is basically deep learning plus anything else to get the job done. and it's trying to mimic human behavior, if that could ever be a thing in the computer. So for us, machine learning is really schoolyard mathematics. It's the things I've just listed here. We've all done algebra at school, and we're going to be looking at that in just a moment. Calculus, don't worry if that's a new term for you. That's just differentiation, areas under graphs, working out gradients. Not doing any of that today. Statistics is essentially categorizing things in the past and probabilities things in the future. And really, machine intelligence, the way I approach it, is if you give something, say, some background information on a job, it could use that background information to do a better job. Like employing somebody to do a job of work. You know, you employ me because I might know something about electronics. But I'll still have to apply all the maths and all the schoolyard stuff I did, 30 odd years ago. So that's really just setting the scene on what it's all about and where we are going to fit in with the Raspberry Pi Pico. Right, now then, you need to buckle in for this next few slides because sharpen your pencils. This is going to be a little bit of a mathorama for a few minutes, but it'll all make perfect sense within 20 minutes, I promise. So the way we're going to approach it is we're going to take some data and stick it into an array, like the example I've got here at the top of the page. And we're going to do a little bit of number crunching, which we're going to look at in just a second, and then try and improve the model and make predictions. And every time we do a prediction, we're then going to go around the loop again. So if I press this, it might do an animation. Go on then, animation. No, that didn't work. Never mind. We're going to do an animation. Sorry, do an update on a new set of data. So we're going to move the data. So just try again, see if this works. There you go, the computer froze. So we just move the data through the array, do some more number crunching, and come up with an improved model of whatever it is that we're trying to predict. And we're going to look at temperature. And then he just goes around the loop again. And that's pretty much all we're worried about doing. So on the Pico, I found a few issues which we'll talk about. It's not all peaches and cream. It's been a bit of a headache in some regards. But we'll have a look at that. So that's the basic model that I've got here for machine learning. And so with your pencils sharpened, let's dig into a little bit of maths on what we're going to use. So the first one is, it says here, linear regression. It's a very fancy way of saying a straight line graph, which I've got the equation for here, y equals mx plus c. M is the gradient, which is the orange line, and c is where it cuts the line. Now, if you took a boatload of data, the equation here at the bottom left of the screen is how it will work out, so it's just mathematics, how it will work out the gradient for a best fit line. So, for example, just this notation here for us. xy, what I'm to say in there is if x was, say 2 seconds, and had an amplitude of, say, 3 volts, xy is 2 times 3, which is 6. And then all the data points on this graph, I think you can see 6 crosses. You just do that for all the data points and plumb it into this equation, and it will give you a best fit straight line equation for both the gradient m and where it cuts the axis. And here it's the bottom left, so you might guess it's 0. That's all you have to worry about for linear regression. Piece of cake. Right, now then. Oh, an n, should say, is the number of samples. So we can put that into a very simple bit of MicroPython code. Right, hopefully that will work. Right, now then, if we're going to do anything in a computer and try and work some numbers out, it's always best if we can analyze numbers that are within a known range. So if we were trying to do some predictions on a gradient, that gradient could be anything from 0 to 1,000,000. It would be very hard to do the mathematics and some predictions. Whereas if we use, rather than a gradient, we use, say, the angle, well, the angle is going to be somewhere between 0 and 360 degrees. So we've got a defined range that we can use some if-then-else computer statements on. And here I've just reduced it with a simple equation. So it's the angle, it's always between -1 and 1. So now I can very easily go, right, well, I now know when I do my maths, the numbers are only going to be within a certain range. And that makes life so much easier. The next little bit of maths is, and I've talked about this last season, called a product moment correlation coefficient. It's a bit of a mouthful. All it's saying is it is a measure between -1 and 1 of how all the data points relate to each other. And this is the magic equation. And if you're worrying about this math is out of this book on your screens, titled Statistics, an Introduction, Teach Yourself. I got this in town in Heifers. That's where I found these equations and I thought, brilliant, that's what I want. So there's nothing new in all this machine learning AI stuff. It's been done donkeys years ago. We're just applying it. So in my equation on my screen, I've just color coded it just so I have no idea how they derive these equations. I don't really care, to be honest. It works. It gives me a number, as you'll see in just a second, between -1 and +1, depending on how the data all relates to itself. So if I press that, there you go. So if the number is +1 exactly, then all the data is in a perfect straight line. Brilliant. If it's all over the place, like here in the middle, you get a 0. Okay, that's useful. And of course, if I get a somewhere between the two, then it might be a little bit scattered. So what I'm starting to build is like a model of the data from different perspectives and seeing how it relates to each other and what all the deviations are. There
Stephen,
yep.
Quickie question. You've got the orange line there,
Yep.
doing various slopes. Has that got anything to do with the value of R? The slope
Yes.
of the line?
Right. Sort of. Right. Very good question, Ruth. Right. Let me dig into that a little bit more. Glad someone's paying attention to my ramblings. Right. So the value of R is actually between plus or minus. If it's plus, it means the grade's going up. If it's minus, it means it's going down. And it's a measure of how well the numbers relate to each other. It's not showing you what the gradient is. It's just how spread out, like in the middle, they're all over the place. So there's just no correlation at all. If they're in a perfect straight line, you'd get plus or -1, depending if the line was going up or down.
I got you.
Yeah. Now there is a problem with this old school maths, but we have to put a fix in our code for this problem. In the middle, if you get a perfect straight line like the one in the middle, you also get an R of 0, even though it's a perfect straight line. Because it's neither going up nor down, there is a small anomaly in the algorithm. So in our code, we'll have to put a trap sequence to try and go, okay, is that a real thing or not? And then that will double. But if we then bring in the previous bit of maths about the angle, so if that gradient angle is 0, but I've got an R of 0, then clearly they must be in a straight line. If that makes any sense. So we've got to come at the data from lots of different perspectives in order to draw a conclusion. And you do that in real life. We apply some sanity check to our number crunching. So here is the conclusion of that crazy whirlwind tour just then. We've got our linear regression, which gives us our gradient, and it gives us a cut where it cuts the x-axis. So we'd use the M and the C for our future prediction in machine learning. But in order to do some maths, we want to end up with an if then else computer statement at the bottom. We want to be within some known range, and a normalized phase and the product moments R gives us that. And then finally, we're going to do a magic term called fuzzy logic, which is logic is usually just on or off, 0 volts, 3.3 volts. Fuzzy logic can be acceptable levels within your code or electronics between the two. So you might have a level of, say, 0.3 or 30% of the supply route, and another one of, say, 60% of the supply route. So you're adding a little bit of granularity to your logic function, and that is an if then else computer statement. And if you put enough of those if then else computer statements together, they've called it a random forest. It's just if then else. So once again, there's absolutely nothing new here at all. Right, okay, everybody breathe. That was fast and furious. We'll slow down a little bit and we will apply it and see it hopefully in action, assuming my demo works. Right, is everyone still with me? Yes.
You're up to 18 now, by the way.
Yep. So everyone's going, oh my God. So really, it is actually, if you break all these problems down, they're actually really quite simple chunks. It's just when you try and take a massive helicopter view, it really can be almost overwhelming. But really, it ain't. Say, teach yourself statistics and introduction. What we've just done is out of that book. Who would think? Got a quick chat here. Let's have a quick peek. Someone said, oh, thumbs up emoji. Okay, that's good. Thank you. Right. Okay. So tell you what, let's apply this to some temperature. So I've got a board, which is this one here on your screen, and I've got it on the camera. I'll pop it shortly when we go back to the camera and some code. I've just got a couple of slides on this just to set the scene for us. So I've circled it at the bottom there in red. It's all these components are just off the shelf, and I've just designed this just so it'll plug neatly into the back of any Raspberry Pi Pico. Nothing special at all. So the data sheet for this chip, I have actually. Why does that freeze? That's good, isn't it? Hang on a second. How do I get that lot? Hang on. There we go. What's that about? Right, so the data sheet for the TMP36 is just an analog temperature sensor. I've put the data sheet in the downloads. This is the important page for us here. So we're using the TMP36, and I've just worked out, let's have a look at it just a second, a bit more detail, what the equation is for the voltage coming out of the sensor and into the Pico, depending on what the temperature is. And as you can see there, the temperature has a gradient of it's 10 millivolts per degree C. And this particular one we've got here starts at 0.5 volt, and for every temperature rise, it's 0.01 of the temperature. So this will go up to about 750 millivolts rather, this sensor. Here's another view. This is a first gotcha, something I've discovered in the last couple of weeks with the Raspberry Pi Pico, so make a note of this. under no circumstances must you ever allow an input voltage, whether it be the ADC or a logic input, to be greater than the supply rail. I had some troubles. I was using a GSM module. For some reason, the designers decided that the operating voltage for the GSM module would be 3.4 volts, not 3.3 or anything smaller. And it's this one here, actually. It's the SIM 800H. 3.4 volts it starts at. If you put 3.4 volts from this into the Pico board, there's a very good chance that it will hang. I had all sorts of weird problems going on with suddenly the code suddenly hanging, and I couldn't work out. I thought there's nothing wrong with the code, so I eventually tracked it down to the RP2040 has no voltage tolerance for being above the supply rail, so that's quite key. The ADC, it is 16 bits. So the ADC value will read is that fancy equation there. So that works out at about 50 microvolt resolution. I don't think you'll ever be able to sort of have 15 volt resolution. I suspect, based on my experience, you're gonna have to write off the first 4 bits, which means you've probably got about an 800 microvolt resolution, which is still over 1,000 levels per volt. So I think that's pretty easy. Right, okay, so bear that in mind. So that's what I've got hooked up, and just on the next slide here, we're going to shove our pin into TMP36 and go into ADC 0. And for those who meant to join us last time, this pin mapping here is what I've worked out will enable you to have a GPIO bus of 8 bits, GP there, an SPI bus, an I2C bus, analog pins, and 2 UARTs. And if you follow that regime, you can still plug in things like the displays that you can buy from the Raspberry Pi shop. We spoke about this last time. Of course, I can't get the thing out of the bag, so I won't bother. But of course, if you go and buy other sensors, it's kind of still every man for himself, like with the Arduinos. It's every man for himself. So don't expect to be able to go and buy a temperature sensor or an environmental sensor and a display and think they're going to be able to work together. I guarantee you will find a pin conflict. So the proposal here actually gets around any pin conflict problem and still gives you full control of any peripherals you want to nail onto it.
Stephen,
Yes.
I've just looked up the ADC value. Sorry, the ADC value might be 16-bit, but the actual ADC physically is only 12-bit, which is why your bottom 4 bits are not so great.
Yeah. Well, there you go. Yeah, you see, so the last 4 bits. But I wouldn't ever trust the bottom 4 bits anyway. You know, any ADC. You know, if you bought an ADC that will say 12 bits ADC, I wouldn't count on the bottom 4 bits being even close to stable.
Yeah, well, my experience was certainly say the bottom bit and maybe the bottom 2 bits. I wouldn't normally throw away the bottom 4, but yes, I take the point.
Yeah. Well, this is my experience as well. So I had the same thing, which is we had some systems that were 16-bit, but they performed identically to 10-bit with the slope converters. Brilliant.
One thing you can do, which might improve resolution, is oversampling. In which case you take a reading and then instantly take a second reading, and you average those 2 together.
You know what? We're going to be doing that in 30 seconds. It's almost like we scripted this.
You're so good.
Yes, in fact, I had to do it for a very practical reason because it just was not working. Yes, right. Okay, I'm almost on cue here. So you're all really welcome to switch your microphones on and chip in thoughts, comments, questions. It's not just me banging on for an hour, unless you're eating your lunch, in which case it clearly is, or your dinner. Right. Okay. So, right. That means time to plug some stuff in and watch it. Hope to God work. So, right, I'm going to totally drop out of this so I can then show you something slightly different. Slide to the links. Right, slide, links to the slide, Jason, is very quickly, hang on a second, we just interlude the questions as we go. Well, in fact, why don't I just actually find it a second? Hang on a second. Let me just get that bad boy link that Jason just said and stick it in the chats for everybody. I should have had that ready. Hang on a sec. Let me just service the chat for a second. So if I hit, come on, downloads. Oh gosh, that's quite slow, isn't it? Right, go on then. Oh no, there we go. Oops, crikey, back. Oh my goodness, that could be faster, couldn't it? Right, hopefully. There you go, Jason, and everybody else. Right, okay, back to the story. Right, stop SlideShare a second. You're all still there, that's brilliant.
Yay!
Right, now then, so what I'm going to do, so hopefully I'll be able to share this with you. Right, let me just share the camera for a second so you can get a view of where have you all gone on my, hang on everybody, I've lost you all. I know you're still there, I hope.
Yeah, you're coming through loud and clear.
Yeah, hang on a sec, I'm having a usability issue for 2 seconds. Zoom, right. Okay, that is genius. All right, okay, you're there. Right, sorry, I'm there now. Things were hiding behind different things on the screen. Right, okay, so let me just explain very quickly whilst I'm gonna do some camera gymnastics. Right, so this is our board. Right, so if I turn that on to get a better picture. There we go, everybody. Right, let me just point out what we've got going on here. And then, so this is the Pico board. This is my development board. I did say last time I had 4 spares of these. They are now at Makespace in my box. There's 4 of them. It's first come, first served. Jason was after one. If you get yourself to Makespace before everybody else. My blue box with my Stephen Clement Silicon Cortex written on it. There's 4 in the top, there's no components on them, but you can sort that bit out a bit later. But what we've got here, this is our Pico, unmodified, nothing special. I've just got some switches and I've got some LEDs as per the schematic which I showed you. And then this is my plug-in board here. This is my temperature sensor. So all I'm going to do in our test, I'm just going to stick my fingers on there to warm that up. And hopefully, as I show you the bit of AI program, fingers crossed, this works brilliantly. Right, okay. So stop sharing that one. And I'm going to attempt to share if I just do that. Right, now then, if I just attempt to share my program. Now, I'm an electronics engineer, really. So for those who are software experts, we just have to be kind. Right, hopefully, is that sharing a Sony display for you all?
It is.
Brilliant, thank you. Sometimes I just need a tiny bit of reassurance. Right, so let me just run through this very quickly. Got about half hour. By all means, ask any questions, and all the things we did half an hour ago at breakneck speed, hopefully you'll go, I see where you're going with that now. So this is my skeleton program here, which I put into comments, and I spent quite a bit of time working with this MicroPython, and I have come across a few gotchas you need to be careful of. We'll get round to them in a moment. There are a few. There is the voltage on the pins is one of them that will cause Sony just to suddenly stop working, and you'll have no idea what's gone wrong. So this is my program. So I'm just going to run this very quickly. So the way I do things is I have an initiation process to start with, where I just blink some lights and I send a hello world message over the UART. So I just know everything's alive and working. And when you're doing debug, it's good to know that the foundation of your debug is actually working before you do anything else. Otherwise, you might be chasing the wrong error. Remember we spoke about an array for the data. So obviously I want to set that up. And I'm going to read the data in continuously. And we're going to do some maths here on linear regression, the phase that we spoke about, and the product moment, squirt the results out, and we'll do some if then else fuzzy logic conclusions. And that's going to be our machine intelligence system. And it'll continually go around that loop, refining its model. In this case, it's going to be every 2 seconds. So, bunch of magic commands, which you need to include. This program's all available to download. I've done all that already. On the download, you'll find this all there, ready to rock and roll, and it works. And I define my pins. So I'm going to use something called Unix time. For those who haven't heard of Unix time, it's a timestamp measured in seconds, and those seconds started counting from the 1st of January 1970. Now, here is the first real gotcha I have discovered with the RP2040. The RP2040 cannot handle large numbers, and it cannot handle very small numbers of X decimal points. It will start to approximate everything at X large numbers and small numbers, and start giving you really screwy results.
Can I just interject here?
Yes.
The problem you're talking about is that the standard library for the RP2040, I think this is the one that's built into the ROM, and is definite, and the ROM library is definitely used by MicroPython because it makes everything smaller. So anyway, the standard floating point library is intentionally not IEEE 754 compliant. In other words, it does what you're saying. It's not. It doesn't have all of those bells and whistles that make it robust.
No.
The chase of actually getting reasonable mathematics performance in floating point on a chip that basically doesn't even have a floating an integer divider. So anyway, that's the way things are now. There's nothing to stop the chip from calculating properly, full-blown fancy numbers, but you just have to tell it to do it. I must admit, I don't right this moment know how, as in, I haven't gone off and discovered how you do it. I would expect with MicroPython, you would need to recompile MicroPython somehow to link with the alternate maths library.
Yeah.
Anyway, that's what's going on. It's not that the silicon is screwy. It's that the maths library has been intentionally modified,
Crippled,
so that you get decent performance.
Right. Okay. So the upshot of that, everyone, is that we need a way to deal with it. Yeah. And the way I found to deal with it, in fact, if you look at the bottom there, you can see just highlighted, that's a Unix timestamp. The way I've dealt with it is, if you remember when I went back to doing those multiplications of x times y, suddenly that's when you end up getting massive numbers if you're using a Unix timestamp. So the way I've got around that is in the array, once I've got all my data into the array, I make the first timestamp 0. And so all the times are referenced off the first timestamp being 0. And that solves the problem for the massive number issue. So I'll show that in a second.
Just in general, when you're doing floating point maths, it's always better to keep the sequence of multiplies and divides roughly alternating, so that you never end up with big numbers.
Oh, that's a clever idea.
In general, this isn't, I think, anything to do with balked libraries. This is in general because floating point numbers have weird behaviors that are not academically mathematical, if you know what I mean. It's unwise to treat a floating point number as if it was an integer with extra precision.
Yeah.
Always try and keep the numbers bounded and understand where you're going with it, because there be dragons if you don't. Yeah. Peter has a question.
Peter.
Floating point numbers are most.
Well, I heard, I don't know, I'm not an expert on this. I heard that keeping them close to 1 it gives them the best accuracy. This sounds like a more complicated question than we need to be answering.
I think yes, it is, and I think there's nothing special about 1, but the problems arise when you, let's say, try to add, one very large number to a mediumly large number, because the difference in scale. You end up with very, very odd results. So it's to do with rounding and approximation, and also the fact that when you convert a decimal number, such as we're looking at here, to a binary number, you do not end up with exact values some of the time. In the same way that decimal numbers can't represent a third properly, binary numbers can't represent some values properly either. And it's those sorts of issues that come into it. So I'll shut up now, otherwise I'll take the whole of the talk.
Okay, that's the gist of what I heard. Yes, there we go. Right, now then, back to the story of doom. So, where are we? Yes, so interesting one for you all here is, what I found is, if you've got the Raspberry Pi plugged into Thonny, and you go and read the timestamp, very neatly it's don't ask me how they've done this. I'm quite impressed with it. But overall, I'll be honest, overall, I am actually quite impressed with what they've crammed into a dual M0 Plus ARM core. You know, hats off to them for it, really. But Unix time, I thought, God, how am I going to convert all of that? But hey, look, they've done it all for you. The line here does it all for you straight out the box. You know, who could ask for more, eh?
Can I, one last interjection? No, it won't be a last one, sorry. One further interjection about Unix time. So Unix time, absolutely 1970 base, number of seconds. There are systems around which use Unix time in a floating point number,
yeah,
with fractional value, shall I say, so that you can represent sub-seconds. And there are also systems around where it's like a Unix time in the sense you're counting seconds from a point in time, but the origin point is not 1970. The ones that I know about is either 1900 or 1980.
There is actually one built into the Raspberry Pi Pico with the origin dates actually 2000.
Yeah, right. So just know, if you care, just know what you're looking at. Make sure it's what you think it is.
Yeah. On the bonus side as well, before we move on, talk a long time about Unix time, is if you get any of this data, from machine learning or anything else, and you store it, say, with Unix time to a file, you can then import that file, say that it's a CSV, you can import it straight into Excel, and Excel has got a Unix time decoder, encoder built into it. So that's handy.
See, how does it know the time? Does it have some Wi-Fi connection? Or?
You know what? I'm not sure, but I noticed this picked it up, and I was quite impressed. I'm like, that's just saved me a whole load of trouble. So I don't.
From your local computer.
Yeah, Richard, just take the win. Anyway, let's move on. We've got a quarter of an hour, and I've still got some things I want to show you. Right. Okay. So, yikes. So I always put things into, I'm a little bit old school BBC land, or try and put as much as I can into functions or procedures, as we used to call them in BBC days. So it's easy to pull the data out and reuse it. And this is what you were talking earlier about, some averaging. I just plumbed for 100 here. And I'm just summing them up and then doing the averaging. Maybe, like you say, maybe do sum and average a little bit sooner. I don't know. Just don't worry about it. It works. And then I'm passing back for the array when I'm calling this function, the timestamp and the temperature, and that's those two bits of data what's going to go into an array. And then we'll see in a second. We'll then do our number crunching on it. Right, let's whiz down. Right, so yeah, so I create array. I've just, in my example here, I've just grabbed 10. I'm just grabbing an array of 10. It's a, what is it? It's a last in, there's a first in, last out. I think that's how you describe it. Yes. Basically, I'm just shifting the data. So it's like a rolling array of data that I'm just updating. I do pre-fill the array, of course, because you've got to start somewhere. So it just does one reading, fills the array. Of course, that's not true data. It'll take probably 10 reads, which are 2 seconds per cycle. That'll be 20 seconds before it's got live data in that it can start doing some analysis. Right, and then I just have an eternal loop. So in my code, I love comments. And when I do code, you'll see I just try and break everything down, because when I come back to this in 6 months' time, I otherwise will not have an absolute clue what I've written or why. Right, that's my array updates of, I shuffle the data in the array, shuffle it all along, one out space, and then I'll just tag on my new read on the end, and then I'm ready to rock and roll for some new analysis. And that's what we've got coming up here next is, So those equations which we had about 45 minutes ago, I've just repeated them here, and then I've just, usually the way I do it, I just try and break everything down. If you try and do all these maths as one massive long equation, I guarantee it will fall over in a heap. So I'm a big fan of divide and conquer if you can. So I've just split everything down into tiny bite-sized chunks, and then I've just got an easy time of it at the end. So that's my code there for the linear regression, just broken into chunks. That's all it is, piece of cake. And at the end, I've then got my gradient. That wasn't difficult. Then for the phase, I've got it phase 90 for 90 degrees. So we can all picture 0 to 90 degrees or 360 degrees, but converting that from -1 to 1 is a little bit harder. So it's just a scaling. That's all it is. And then, of course, we've got our product moments. Now, this is when I've got another gotcha, is that because of this average, this rounding and inaccuracy, I found occasionally I could end up with a square root of a negative number, which it didn't like because it's not very good at complex numbers. Or I'll get a divide by 0, which is never a good look. Or I'll get a product moment which was greater or less than +1 or -1, which is also not a good look. So I've had to put a few traps in here such that if things aren't quite as they should be, then they're probably, if it's more than 1 on the product moment, it probably should be 1. It's only just tipping over. It wasn't crazy off, but it was enough of to think, well, wait a minute, that shouldn't be more than 1. That doesn't make any sense. So I've just had to put some traps in just to rein it all back in to make a little bit of sense for the maths at the end.
Can I just make a very useful comment, I hope? So in this, in general, floating point numbers, you do not check for equality with a specific, any value. It is highly likely that perturbations will result in the value that you think you're checking for not actually being exactly that value.
Right.
In the code that we've got here, line 202 is the flag, I presume, that you're talking about. So the 205
this is my flag check. I hope that's highlighted.
Oh, right.
That's my flag.
Okay.
If life is good, it'll do the sum normally. But if when I do it on a piece of paper, if I got that perfect correlation of data, obviously the standard deviation will be 0. Now, if I try and do a divide by 0, I tend to get infinity, and the world's a very sad place. So it's those sort of things which I've had to then put some traps into my code to try and catch it. So I'm not really a software programmer. I'm really a hardware guy who's dabbling.
All I'm saying is that small perturbations in the input data can have unfortunate consequences when you try and compare. So pretty much always when I deal with floating point numbers, I'll do a range check. So I'll say, is the value between -0.00001 and +0.0001, rather than is it 0?
Right. Yeah. Oh yes. Yeah. You always want to make sure you try and capture every eventuality. It's like when we do Boolean or state machine logic. We haven't done that on any of our courses, but if you're doing a state machine, you want to make sure you do actually have every eventuality covered. Otherwise, you can end up in a very messy place, which is called a race hazard. Which very first job I had in Cambridge, there was a race hazard. Called thermoelectron. I'm making that up. I don't really know the code anymore. But yeah, they had a race hazard because they weren't capturing everything properly. Anyway, and at the end, this is my fuzzy logic at the end. So they're my magic numbers. So that's all just a code implementation of the maths. and I'm sure, I hope most of you will agree, it's not as scary as what it first looked an hour ago. And then on the end of it, I've just got some fuzzy logic, in fact, we're just discussing actually, of making sure I do capture every eventuality and be able to sort of create a conclusion for it. Now, these conclusions are from observations that I've made when I've been running it. So you might say it's like the learning phase of machine learning. Ideally, what you would do if you're developing a whole system, you would probably make these numbers here would probably eventually over time, maybe you'd move them around a little bit, if I'm seeing too much of the low end, I might want to move the goalposts around. Obviously, I've just hard coded this. And that's it. And then it waits 2 seconds and then round it goes again. So fingers crossed, if I press play and move this screen here, hopefully we will see it updating. We're looking at the bottom lot, by the way. So what I've done here, so this is my data, so just the sample numbers into my array, my Unix time, my reference Unix time, obviously they were 2 seconds apart, and then what temperature it's measuring. This, of course, is this is an average of 100 samples, a bit of filtering. And then I've got here, tell me what the average is, what from that linear regression, what it thinks C is the cut in the axis and what it thinks the rate of change is. And then that rate of changes also can be expressed as an angle, or the 0.23 of a degree. And I've just scaled that. So I'm then doing my fuzzy logic just on my last two here, which is between a normalized, I've called it normalized for -1 to 1, -1 to +1, and the product moment. So my bit of number crunching here is on this one here. And then depending on that, I then would make a decision on how much confidence have I got in the data. So if I was to warm that up between my fingers, hopefully we'll see the average temperature hopefully start to increase. Look, so the degrees per second is increasing, and it's still got a pretty high confidence there that it's increasing at a fairly constant rate. And it's continually going around that loop and updating that equation all the time and coming up with a new prediction. And then it'll probably then, hopefully take my fingers off, it'll slide back down. So that works. So there we go. Have I got anything on my other slides here? Just whilst you're looking at that, enjoying that slide. Oh, right, okay, now I'm doing next. Right, give it that a sec. Okay, any questions on all of that? I've got one last thing to share with you, which is a question from last week, which Jason asked me. So I will be just touching on that for 2 minutes. Any questions or thoughts or comments?
I've just thought of something.
Go on then.
Yeah, just a minor aside, because we were talking so much about floating point numbers earlier. Python is quite interesting in that it tends to shield you from that. You absolutely can represent numbers like 0.1 and so on in as floating point in Python. Not sure how it works, but it does.
Right. Okay. Right.
I remember someone talking. I don't remember the exact coincidence, but they were talking about how, I think it was a Kerbal Space Program discussion about how they would use integers rather than floating points because of the loss of precision can really affect you when you're out on the edge, when you're exploring very far away.
Yeah. That is definitely a thing. That sometimes you just want a known number of digits precision rather than mantissa and exponent. Sorry, not mantissa, and the integer part and the fractional part, rather than the floating point representation, which has an unknown precision. So yeah, it also explains why
stick to integers. But I mean, I suppose, processors have developed, haven't they? And you've got 32-bit processors now, and maybe it's less critical than it was in the past to stick to integers.
I think it's just one thing to keep in the back of your head that if you're there may be situations where you're on the edge of so I think this is something close to it. I don't know if people know about gyro lock if you're measuring angles. So if you have an accelerometer and it's close to the North Pole, if you're using certain types of coordinate systems, the numbers could change very rapidly for very small changes in position. And it can cause all sorts of problems. And they had this during Apollo missions, I think, that you call gyro lock, where the things would get out of control. And so stuff like that zero gradient line is maybe similar to gyro lock, that it reads as the R value is 0, but it's also well defined.
Yeah, well, that's why in here I've got take the angle as well. I think the magic phrase is called multivariant. I think any statisticians in the room will tell us that's the term that they use. What I try and do whenever I'm trying to come up at these problems from multiple angles is not to try and show the data from I would say not to wrap the same data in a different way. A little bit like you don't want to see the data as a pie chart and as a bar graph, because an error in one will be an error in the other. My preference is, well, look at the data from different perspectives and what can you learn from it and draw conclusions and predict. But you've got to analyze that data from different perspectives and not just put a new wrapper around. Like I say, you don't want to be just looking at it from a pie chart and a scatter graph, because you've not really learned anything. Whereas something like an angle and a gradient and the product moment, and I'm sure there's other ones which I'll be tinkering with over the next year, gives you that completely whole new perspective to be able to have some confidence in what you're then predicting.
Yeah, so don't look for the one true way of doing everything.
Correct. And a few years ago, before COVID, I can't remember the company, one of the companies at Eagle Lab gave a talk, and they spoke about coming at the data from 9 different perspectives to have a degree of confidence that you wasn't talking hogwash or predicting nonsense. I don't know if they made that number 9 up or not. I'm not sure where it came from, but it was a few at any rate. And I struggle to get past 6 at the moment.
I think it's that what you're talking about here is similar to if you try and triangulate a position on a map, and you take compass readings of it from 3 places, which is the minimum, obviously. It's quite common when you actually plot those things to end up with not a single point in the middle where your object is, but a small triangle in the middle representing your uncertainty, the error in your measurement. And if you then go off and take, let's say, another 3 measurements of exactly the same point, you will be able to reduce that error to the likely place. But again, if you look in sufficient detail, you'll probably never get to the point where you've got it on the spot. There always will be an error. It's just how big an error do you want to, or can you cope with?
I think, Ruth, that's exactly correct, because I spent some years teaching experimental stuff to physicists, and they're saying, no, but what's the right answer? And you're like, well, it's like here.
Yeah.
And people react to that differently. They think it's a trap. They think it's doing it. But one of the most interesting lab reports I ever read was where someone nailed Planck's constant to several decimal places, and you never sit at the conclusion section of the lab report, which it wasn't me, I didn't do it. That's not what happened. So and dealing with uncertainty is actually a really difficult conceptual problem that you need someone with hands-on experience, theoretical. It's not. People tend to think, oh, you'll get the right answer if you did the right job, and that's not at all how the world works. You need to be able to be flexible.
What I want people to take home from this talk of floating point numbers, which is rather a long way from where Stephen wanted to take this, but there you go. But anyway, what I want people to do is to take away the idea that floating point numbers have difficulties. They're not magic things that just automatically do what you want them to do. Just like everything else, there are things that you should be aware of. And as somebody said, if you can use integers, integers are generally a lot easier to deal with. If you can use a fixed point integer, then they are slightly easier than floating point. But sometimes you need floating point, and in which case you just understand their limitations.
Steve,
Right.
That box link you put in earlier just seems to give a oops, we can't seem to find what you're looking for.
Brilliant. that went well. Right. Okay. Bear with me. Right. I tell you what. That's very neat, because I just want to crave 2 more minutes of your attention, and I will finish up with a more reasonable answer to that duff link I gave you all, which is just a test. So bear with, because what I want to do now is I don't just want to close off that now, because what I would like to do, I'm running over, but last time we were out, I was asked about how to connect a second Pico, and I've had a look at it, and it'd be a bit remiss of me not to share that all with you. So I've had a look at this, and it's not as straightforward as what you might think. Right, hopefully you can all see that on your screen, yeah? Yes. I think that's a yes. Right. So you see that okay, can you? That whole screen?
Looks good to me.
Good. Right. So question is, I was asked last time very quickly, I think it was by Jason on the call here, of how can you connect a second Raspberry Pi Pico? Can I just stick it upside down and solder them all together and life is good? The answer to that is no, you can't. I've had a look at it. You need to do a small number of modifications. And let me just show you what those modifications are. There we go. I can see that better now on my screen. So there is on the Raspberry Pi Pico board, there is a small diode called D1. You've got to take that off. And also, before you solder that black header in, as you can see there, the 3 pins, you need to pull them out, so you're not soldering to those. And there's also then a small bridge, as you can see, linking 37 and 38. Now, what that's all doing is it's disconnecting the 3v3 rail power supply on one board, so it can then take its power from the other one. And TP6, if you had them all stuck together, you could actually just put a wire link between the TP6 pad that I've connected a switch to, and you can just touch that to any of the grounds, and that'll be the same as hitting the boot select. Because if you've got them all sandwiched together and you're drawing power from one of the other board, you might not be able to get at that boot select switch. So either what I've done here, I've soldered a small touch switch onto the bottom, or you just need to touch TP6 to ground and it'll go into boot mode. I've got the schematic in a second just so you can see that a bit more clearly. And the LED, I just moved it onto the back. The LED actually comes out on TP5. So those pins on the back of the board are clearly for the manufacturing to be able to test it. So just making good use of it, really. So if you do all of that, you can then stick them both together, and you've then got a quad M0 plus core. And this is a schematic. So taking D1 out, you can see here on the screen, that just disconnects. So when you plug in the two USBs, you're not then powering up the switch mode regulator. And I also connected the 3v3 enable to ground, although if it's not got power, it's probably not doing anything. But just for good measure, I connected it to ground with a link. So that's the modification I think you need to make if you just want to stick two Picos back to back. And then the last thing on here is when you go to Thonny, you'll then have, as you can see here, if you go to Tools and Options, you'll then be able to select which of your two Picos you then want to connect to and program. So you might just have to do a bit of experimentation in order to work out which one is which. But Thonny can only handle one Pico at a time. You won't be able to have multiple ones in the same program. What I didn't try, and I have no idea if this will work, if you have a second installation of Thonny, can you then have one on COM3 and one on COM6? I don't know. Maybe. Didn't try that. So there's the answer to how do you connect a second Pico. And I did notice, I think next February, when we'll talk about co-processing, we'll come back to this next year and see what we can do to offload some of this number crunching onto another processor. Particularly if you're doing frequency analysis, or sound or something, you might want one of the processors doing all the number thinking and just giving out a result, and then the other one doing slightly less work.
I think if you're actually seriously into doing floating point stuff, the Pi, so the Pico is not the greatest processor on the grounds that it has no floating point hardware. Your better bet would be to go for something like the SAMD series. I think SAMD 21 is quite commonly available, which have instead of a Cortex M0, they have a Cortex M4.
Okay, well that's better, isn't it? That's got a proper floating point arithmetic.
And that's got the proper floating point hardware.
Yes, it does.
What you're gaining there is a much faster floating point. As I said earlier, it's not that the Pico can't do correct floating point, it's just that it can't do it quickly.
Yes. Anyway, that was the answer to a question I was asked last time, so I had a quick look at it and I thought, oh, it's not just a case of stick two together and life is good. No. Right. Okay.
Hello?
Yep.
Hello? Can you hear me?
Certainly can.
Yeah, I don't think I was spotted before. I just thought I'd butt in, unless you were about to tell us something more. I've got a question and a comment. The question I put in the chat earlier. How long does the ADC take to deliver a new reading? And the comment is, I believe in the earlier days of microprocessors, pre-floating point, people use something called scaled decimal, which as I understand is a kind of poor man's floating point, poor person's floating point, where you kind of handle it all yourself. I haven't done it myself and got a hazy idea how to do it, but would that be a possible solution? Well, two questions really.
Right, I'm not sure about the first one. Second one rather, maybe someone else could help with that. And the first one, I don't actually know how fast the ADC is. I made a note here. I will endeavour to have an answer to that question next time we all gather. So
scale decimal can be quite good, but you need to really well define what accuracy you want and where you want it, so that you don't end up with too big a steps between numbers. So for everyone else, I think that means using integers only, but then saying, oh, 1 actually means a tenth, or 1 means a hundredth, or 1 means a thousandth.
Yeah, I imagine it has to be used within a very well-defined scale.
Yeah.
Range of numbers.
Yeah, no, it's interesting because NASA, there was something about NASA only uses pi to a certain number of decimal places that's quite small. And that's been enough to get into Pluto. So it's one thing where you need to work out what's going on and like actually run the numbers.
So the I believe what Greg is calling a scale decimal is what I was calling fixed point.
Okay.
And
sorry,
one of the nice things,
my mistake.
It's all right. It's not. Yeah. One of the nice things about fixed point is that the mathematics works fine. Integer maths works fine on fixed point. It's just a case of remembering the scale when you input and output. So you can do the maths just fine on fixed point, and then you have to remember to scale it properly when you enter your numbers, and scale it properly when you print them out or store them or whatever.
So a lot of this is about defining the problem accurately and then testing that it's delivering the results you think it should be. I mention that because there was one thing where I was taking some data back when I was at university, and it all kind of went up, but then Excel drew a trend line that was completely like opposite to what we were doing, and we couldn't figure out why. And what we realized was one of the data points went down a long way. And what Excel had done was average the difference between data points, popped a line through it, then analyzed does that fit the bill well enough for me to report a result? And it said yes. So it then reported that the fit line was actually 90 degrees to what the data was suggesting. And we never figured out how to get around that. But it was interesting that even we saw it in MATLAB, we saw it in Origin, which is a scientific, basically all the major packages had this problem in them and it wasn't acknowledged. And I think they would call it a case of regularization, but that's where my knowledge is, that's the edge of my knowledge, and beyond that is gone. But it was always really check what comes out of any algorithm before you use it.
Yeah. The answer to the question on the ADC speed is at the fastest that the ADC on the Pi Pico can cope with, it takes 2 microseconds to fetch a value, which is 96 clock cycles of the 48 megahertz clock that is used internally for such things. So that's not 96 processor cycles, because that's different. And if you put 2 microseconds the other way around, it's 500 kilosamples per second.
There we go. Thank you. Right. I know something as well. Right. Okay. Look, ladies and gentlemen, it's 8:45.